You've probably heard that airplane cabins are pressurized. It's one of those facts people accept without ever questioning it. But here's what almost no one asks. Why isn't the cabin pressurized to sea level? If engineers can control the pressure, why not just replicate the conditions you'd experience standing on the ground? The answer isn't simple. And once you understand the actual engineering logic behind it, you'll realize this is one of the most carefully calculated trade-offs in all of aviation. Let's start with the problem itself. The cruising altitude of a modern commercial airliner is typically between 35,000 and 40,000 feet. At 35,000 feet, the outside air pressure is roughly 23 kilopascals. At sea level, it's about 101 kilopascals. That's less than a quarter of what your lungs are used to. Without any pressurization at all, passengers would lose consciousness within minutes. Hypoxia would set in fast. The body simply cannot extract enough oxygen from air that thin. So pressurization isn't a comfort feature. It's a physiological necessity. Now here's where the misconception lives. Most people assume the cabin is kept at sea level pressure, 101 kilopascals, the pressure you'd experience in your living room or on a city street. It sounds logical. If the goal is passenger comfort and safety, why not replicate ground conditions exactly? But that's not what actually happens. On virtually every commercial airliner in operation today, the cabin is pressurized to an equivalent altitude of approximately 6,000 to 8,000 feet. Not sea level. Not even close to sea level. The cabin of a Boeing 787 at 40,000 feet feels like you're sitting at around 6,000 feet above sea level. A standard Boeing 737 or Airbus A320 is typically set closer to 7,500 to 8,000 feet equivalent. That's roughly the elevation of a high-altitude city. Denver, Colorado sits at 5,280 feet. Mexico City is around 7,250 feet. Your body tolerates those elevations, but they are not neutral. There is a measurable physiological effect. So why is the industry standard set here? Why not sea level? The answer comes down to one word: differential pressure. To understand why this matters, you need to think about what pressurization actually requires structurally. The fuselage of a commercial aircraft is essentially a pressure vessel. It's a sealed tube that must contain higher pressure inside than exists outside. The difference between those two pressures is called the pressure differential, and it places the fuselage under constant mechanical stress. Every flight cycle, every takeoff, pressurization, cruise, depressurization, and landing, the fuselage expands slightly under pressure and contracts again. This repeated expansion and contraction is called fatigue cycling, and it's one of the primary reasons aircraft have finite structural lifespans. Here are the actual numbers. At 35,000 feet, outside pressure is approximately 23 kPa. If you pressurize the cabin to sea level, 101 kPa, the pressure differential is about 78 kPa. That's 78,000 pascals of outward force acting on every single square meter of fuselage skin. Now consider that a modern wide-body aircraft has hundreds of square meters of fuselage surface. The structural loads become immense. The fuselage walls must be thicker. The frames must be heavier. Joints and window surrounds must be reinforced far beyond what would otherwise be necessary. Every kilogram of added structural weight costs fuel across millions of flight hours. The economic penalty is not trivial. It's enormous. Now run the same calculation with an 8,000-foot cabin equivalent. Outside pressure, 23 kPa. Cabin pressure at 8,000 feet equivalent, approximately 75 kPa. Pressure differential, around 52 kPa. That's a reduction of roughly 33% compared to sea-level pressurization. The structural loads decrease significantly. Fuselage walls can be thinner and lighter. Fatigue life improves because each pressure cycle subjects the structure to lower peak stress. Over thousands of flight cycles across a 20 to 30-year aircraft lifespan, this difference is what separates a structurally feasible design from one that would require constant heavy maintenance or early retirement. This is the fundamental engineering trade-off. Every kilopascal of additional cabin pressure you add requires more structural weight and accelerates structural fatigue. Every kilopascal you remove moves passenger physiology closer to hypoxic conditions. The industry settled on the 6,000 to 8,000 foot range because that's where the two curves cross at an acceptable point. The human body tolerates those elevations without supplemental oxygen for hours. Healthy passengers may experience mild fatigue or mild dehydration, but there's no acute physiological danger. Meanwhile, the aircraft structure benefits enormously from the reduced differential. There's a secondary layer to this. The air used for pressurization has to come from somewhere. On most conventional aircraft, virtually every commercial jet except the Boeing 787 Dreamliner, pressurization air is bled from the jet engines. Hot, high-pressure air is extracted from the compressor stages of the engine, routed through cooling systems, and fed into the cabin. This process is called bleed air extraction. It's effective, but it comes at a direct cost. Every kilogram of air bled from the engines is air that isn't being used to generate thrust. Bleed air extraction reduces engine efficiency. It's a parasitic load on the propulsion system. The more air you extract, and the higher the cabin pressure you try to maintain, the more engine performance you sacrifice. Again, the 8,000-foot standard represents a balance. Enough pressurization to keep passengers safe and reasonably comfortable. Not so much that bleed air demands become a significant drag on performance. The Boeing 787 took a different approach entirely, and it illustrates exactly how much the industry was constrained by this trade-off. The 787 is built primarily from carbon fiber reinforced polymer composites rather than aluminum. Composite materials behave differently under cyclic pressure loading. They don't suffer from the same metal fatigue mechanisms that aluminum fuselages do. Because of this, Boeing was able to increase the pressure differential the airframe could tolerate without an unacceptable weight penalty. The result? The 787's cabin is pressurized to a 6,000-foot equivalent rather than 8,000. Passengers consistently report feeling less fatigued after long 787 flights compared to equivalent journeys on aluminum fuselage aircraft. The 787 also uses electrically driven compressors for pressurization rather than engine bleed air, eliminating the parasitic efficiency loss entirely. These two changes together, lower cabin altitude and no bleed air extraction, are significant engineering achievements. But they were only possible because the composite structure enabled a higher pressure differential without proportional weight penalties. The pressure differential also defines one of the critical failure modes that pressurization engineers must account for: rapid decompression. If the fuselage integrity is compromised at altitude, whether through structural failure, explosive decompression, or window failure, the cabin pressure can equalize with outside air almost instantaneously. At 35,000 feet, that means passengers are suddenly exposed to 23 kPa of pressure. Useful consciousness at that pressure without supplemental oxygen is measured in seconds. This is why commercial aircraft carry supplemental oxygen systems, and why oxygen masks drop automatically when cabin altitude exceeds approximately 14,000 feet. It's also why the FAA and aviation authorities set regulatory limits on maximum cabin altitude during normal operation. 8,000 feet is the regulatory ceiling, not an arbitrary design choice. Going above that in normal operation creates unacceptable physiological risk in the event of any pressurization anomaly. There's one more layer worth understanding. Pressurization doesn't just affect structural loads on the fuselage. It affects windows, doors, cargo holds, and every penetration through the pressure vessel, every wire bundle, hydraulic line, and control cable that passes through the fuselage wall. Each of these is a potential leak path. Each must be sealed and certified to maintain integrity across thousands of pressure cycles. The engineering complexity of a pressurized fuselage is substantially greater than people typically appreciate. It's not simply a tube with air pumped in. It's a carefully sealed structure with every interface engineered to a specific leak rate, certified across a defined service life. So when you board a flight and feel that slight pressure change during climb, what you're feeling is not a malfunction or poor engineering. It's the result of a deliberate, mathematically precise decision made decades ago and validated continuously since. The cabin is not at sea level because sea level pressure would require heavier structure, accelerated fatigue, higher bleed air extraction, and greater fuel burn, all without meaningful benefit to a healthy passenger. The 6,000 to 8,000 foot standard is where structural efficiency, engine performance, and human physiology intersect at an acceptable point. That's not a compromise in the negative sense. It's precision engineering. The next time you feel slightly drowsy on a long flight, it's not just the recycled air or the lack of sleep. You're sitting at the equivalent of a small mountain. Your body is working a little harder than it does at ground level. And the reason for that is written into the stress equations of every aluminum frame station along the fuselage. That's the real answer. Not magic. Not oversight. A trade-off calculated to keep a metal tube intact across 30 years and 60,000 flights while keeping everyone inside alive. If you've ever wondered why aircraft windows are so small compared to, say, a passenger train, that's directly related to everything we just discussed. I've covered the structural engineering behind aircraft window design in another video.